following refinement of the theorem of Birkhoff that I mentioned yesterday. This is sometimes called Birkhoff's ergodic theorem. Sorry, I was going to give some example first. Sorry, let me just quickly give some examples. So examples of ergodic measure. Right, so examples. Ergodic and non-ergodic. Measures. So as I said, there's really very few examples that I can just give easily. You know, ergodicity is one of the biggest problems. So first example, as I said before, if f of p equals p, okay, this implies that delta p is invariant and ergodic. Okay, so delta p is your f. This is ergodicity is obvious because every set has measure 0, 1, so in particular every invariant set, and we know that it's invariant. Periodic points, right? So if you have a periodic orbit P1 Pk, of period k, then it's quite easy to see that again if you just take mu equals the average okay, this is ergodic and invariant. We already showed that that's invariant. And to be honest, that's pretty much it in terms of measures that are easy to see that it's ergodic. Okay, all the other examples that I know will require a significant amount of technology, which is what we're going to start next week. We're going to start discussing that. Some easy examples of non-ergodic measures. Right, so non-ergodic are the examples that I said before. If you take the identity map, right, then Lebesgue measure is clearly not ergodic. Right? Every measure is invariant, and Lebesgue, the only, for example, on 0, 1, follow the circle, something like that. Then Lebesgue measure is invariant, because every measure is invariant, but Lebesgue measure is not ergodic, right? Because we can just take any set. So f minus 1 of a equals a for all a, and so you just take a set of positive measures and you decompose it into two. A little bit less trivial example is this following map, one-dimensional map. So let's look at 0, 1, 1 half, 1 half, 1 over 4, 3 over 4. Okay, so this is again piecewise affine map. Right here the slope is constant. What is the slope here?
What does this do?
-2, right? Because this is 1/4, this is 1/2. Here the slope is +2. Here the slope is -2. Okay, so you can see that the Lebesgue measure is invariant. right? In the same way as we showed the other time. So if you take a set A here, you see that it has two pre-images here and here. Right? Each one of which is a half, and so on is the same thing. If you take it here, then the two pre-images will be here, but it still will have the same size. So the Lebesgue measure is invariant. Is it ergodic? It's not ergodic because you can see that the interval 0 to 1/2 maps into itself, right? F minus 1 of the interval 0, 1/2 is equal to the interval 0, 1/2, right? So 0, 1/2 is exactly a fully invariant set, right? Because if you look at the pre-image of the whole interval 0, 1/2, it maps exactly to itself, okay? And so this mu of the interval 0, 1/2 is equal to 1/2, which is not between 0 and 1. So you can decompose Lebesgue measure into two measures. So you have the set 0, 1/2, its complement 1/2, 1. Okay, they intersect in the boundary, but this is just a set of measures 0, so they are essentially disjoint sets, A and the complement, modulo 0. And so you have the situation that I described in the abstract setting before, in which you really have two dynamical systems that are independent, right? You see that if you have, for example, an observable, right? If you take these averages, if you take an observable calculated in some orbit xi, you know, if this point is in here, then all that matters is the value observable in 0, 1/2. If the point is here, it's only going to see the values of the observable that are here. So these are two distinct dynamical systems. If I make a change, if I change a little bit the map here, the only people who are going to know, the only points who are going to know are the other points in here. These points do not see that change at all. They're really two separate systems. So this is the easiest way in which you can fail to have ergodicity. But again, this is a fairly trivial example, right? In this case, you fail to have ergodicity because you can see these are really two regions of phase space that are disjoint. Something is happening here, another thing is happening here, and they're not really related to each other. Any questions? So, yes?
But if you have like a finite number of finite orbits and like fixed points for your system, does it tell you something about like that you can find? Because there seems like a kind of dichotomy. If you want something absolutely continuous, you have to not have like too many deltas. To be, I mean, something absolutely continuous to be an extreme order.
Sorry, try to formulate the question.
Okay. So it seems that if like you have many deltas available, so that you can like approximate many things, and they are.
So deltas, you mean delta measures?
Delta measures.
Yes.
That are ergodic. Automatically, it seems to like exclude that if you find something absolutely continuous to that measure, that's ergodic.
So we will show, the main result we will show next week is that each of these components is ergodic. And if you take 10x mod 1, the Lebesgue measure is ergodic. If you take irrational circle rotations, the Lebesgue measure is ergodic. If you take the 10th map, the Lebesgue measure is ergodic. So, and these maps have infinitely many periodic points as well. Right, like 10x mod 1, remember 10x mod 1 we saw, 10x mod 1 has infinitely many periodic points. On each periodic points we have these ergodic measures, right? And then we also have the Lebesgue measures ergodic. In that case, I don't know if this addresses your question or not. But we shall see that, yeah. to be honest, as I said before, and I want to insist again, this is really, even though this has been going on for decades, there is very little results about ergodicity. I mean, when I say very little, there's lots of results. It's a major issue that people are somehow working around and so on, but in the end, it's still one of the most difficult things to find even non-trivial examples of non-ergodic systems and techniques for proving ergodicity. It's really not easy. It's a very interesting. I'm going to give here one approach that works for one-dimensional maps, and then there's other approaches that have been developed. So, for the moment, let's prove these results that tell us why we're interested in ergodic measures, right? And why are we interested? So the crucial result that underlies the theorem is this one. So we have everything here is measurable. We have mu is ergodic invariant measure. And then for all phi in L1, so remember we defined yesterday this limit. Phi in xi, so this is the point phi evaluated along the orbit. So you can think of it like this. So this is our space x. This is phi. This is the orbit. Right? And sometimes we call this the time averages of this function along the orbit, right? Because you're looking at time, you're iterating this point, and this phi has certain values at different places in your phase space, and so you are looking at the averages of these values of phi, right? Phi is sometimes called an observable. It's what you observe in some sense, okay? It is a way to give weights, again, at different points of the phase space. So what I claimed yesterday was I said Birkhoff's ergodic theorem says that this limit exists almost everywhere, right, for an invariant measure, so that somehow this average converges, and now if we assume that the measure is ergodic as well as invariant, we know exactly what it converges to, and it converges to average value of phi, which we sometimes call the space average of the observable phi. Right? So, as you know, you can think, since mu is a probability measure, this can be thought of as the average value of phi. Right? So this integral conceptually is the value that phi would have if it was a constant function. Right? It is the average value of phi. So in particular, what this means is that the orbit must somehow must be uniformly distributed. In some sense, this is what's saying with respect to this measure, right? Because what this integral tells you is the average value of phi weighted by this measure, right? So phi may have, phi is just a real valued function. It might take values which are very large here. It might take values which are very small here. It takes different values around the space, okay? So this measure is focusing on certain regions of the phase space. So this measure gives measure to certain regions of the phase space. And as you know, okay, I don't need to tell you, but what this integral is doing is kind of matching up phi, the values of phi and the measure, right? And is integrating the observable means finding the average value with respect to this measure, right? This is just standard integration, Lebesgue integration. So what this is saying is that if now you look at the orbit, it is visiting regions of phase space. It has a statistics that is defined by the measure mu, right? So if mu has large measure in some region, then this will visit mu many times, and therefore the value of phi, every time that xi is in a particular region of phase space, it will take on those kind of values. Right? So again, we have basically the same corollary that I gave. What I've just been trying to say to give an intuitive explanation is easiest when you take phi equals to characteristic function again, right? And then exactly as we said last time, what the characteristic function means here is the limit as n tends to infinity. So is that, yes, so limit n tends to infinity of 1 over n, the sum of the characteristic function of a in xi, I equals 0 to n minus 1. This is just equal to the number of times between I from 0 to n such that xi belongs to a divided by n, right? And what this theorem says is that this converges to the integral of the characteristic function of a d mu, which is just exactly the measure mu of a. Again, I think this corollary is really the most striking way to visualize, okay? So in many applications of Birkhoff-Cyclonic theorem, you really need this more general version for N1 observables, but what really helps us to understand what's going on is this, right? So this means that you take a set A, right, that has a certain measure, and what it says is then for mu almost every x, the proportion of time, so for almost every point, the proportion of time that the orbit spends in A converges exactly to the measure of A. So you can see that this is a very powerful theorem. This also helps a little bit to understand your question earlier about Poincaré currents and this example of the gases, right? Of Boltzmann gases. The configuration where almost all the molecules are on one side of the box has extremely small probability, right? If you think of just everything being in a random position, you have extremely small probability of that. It has positive probability, but extremely small, okay? So if you take an arbitrary configuration, the proportion, it will land, if you start with an initial configuration where everything is everywhere and you let it run, right? It will visit that, but it will visit that for the proportion of time that converges to the measure to the probability of that configuration, which is extremely small. Right? So if you take a set that is very small, then almost every point will spend very little time in that. Right? The measure describes that. Any questions about this? So this is usually Birkhoff's theorem is not separated the way I have done it. Again, there's several results which I have formatted in a slightly different way from usual, but I think it's important, it's usually stated like this, right, for ergodic invariant measures, but I think it is useful to remember that the convergence of the limit does not use ergodicity. That's why I separated it into two. The convergence in some sense is the most important. In fact, the proof of this is just a few lines after the real proof is about the convergence. And then the fact that if you add ergodicity, you actually know the limit is almost a trivial fact. Although it uses a little bit of the proof of the convergence, so I'm going to skip, as I said, I'm going to skip the proof of Birkhoff's ergodic theorem and Birkhoff's theorem before. I'm not going to include them, because I don't think they add so much to the, going through the technicalities of the proof. But,
can you
yes,
present it like a double integral using the characterization?
excuse me?
Can you present the limit like a double integral using the lemma that you showed before about the moment? Something.
It's much simpler than that, actually. It's just that the ergodic measures.
No, I mean for the generic invariant measure.
Oh, for the invariant measures, that is really a, no, that, to be honest, part of the problem is I'm not able, and I've never had anyone be able to give a heuristic description of the proof of Birkhoff's theorem. Heuristic in the sense, okay, it works like this, it's just technical proof. Maybe some people are able to give it some meaning, but I am not able to really say what is the philosophy behind the proof, what are the steps of it. But it is in my notes, the complete proof, so you can have a look at it. But of course, it's the convergence that is the most non-trivial thing. Although the convergence without the understanding of the limit doesn't give much. And in fact, now you can see that the reason why you cannot do this is because, of course, if the measure is not ergodic, right, then you cannot go from one side to the other, right? So when you look at the integral of phi, it's going to take the average value of phi over the whole space, okay? But suppose that you have these two invariant sets A and A complement, on which the dynamics is completely disjoint, right? Then if you take an initial condition here, then it's going to stay in here forever, and all that matters is going to be the average value of phi here, right? Not the average value of phi here. So this here does not, it's impossible that this is going to converge to this, because you can change the value of phi here, and it does not change the value of phi here, right? So this is why ergodicity, the indecomposability of ergodicity, is telling you that actually these must visit the whole space. When I say the whole space, I always mean the whole space viewed with the measure mu. Again, right? This is important because you fix a measure, and so every time you fix a measure, the whole space, it could be that this measure mu gives positive measures just to some subset here, and then what I mean by the whole space is just what happens here, because everything else has zero measure, and it does not, even when I say, okay, this is for almost every, it's not, again, right? So it could be that, so what this says here, the fact that the measures are ergodic and therefore you cannot split it into two pieces, means that every point visits in some sense, the full support of that measure, the whole space where that measure is. Right? So every time you fix a measure, and then your whole space means your whole space with respect to that measure. So as you correctly, I don't know if this is what you were kind of thinking, but in general, you will have lots of invariant measures, lots of ergodic measures, right? So each time you choose one, okay, and then this theorem is with respect to that measure. So you're choosing which lens to look at the system from. This would be another way we look at particular cases, particular applications. You really want to know, okay, which measure do we we choose. Okay, so we're running a little bit late. Let me say that a second corollary of this is that if, again, under the same assumptions, we have that if phi, so for all phi continuous, we have that limit to infinity of integral phi d mu n x naught so we're d mu n x naught. So I'm going to kind of give you the proof inside the statement as well, right? So let me write this as equal to the limit of n integral phi d. So this is 1 over n, the sum of the Dirac averages. Right? This is the measure, mu n is this measure, right? Mu n of x naught, and this is equal to, so we can distribute this measure, so this is equal to the limit n to infinity of 1 over n of the integral of the sum I equals 0 to n minus 1 of the integral of phi d delta xi. So you can just distribute it here, and of course you know when you integrate with respect to Dirac delta measure, this is just the limit n tends to infinity of 1 over n, the sum I equals 0 to n minus 1. So the integral of phi on Dirac delta measures is the value of phi at that point. Right? So this is phi in the point xi. And this, by the Birkhoff theorem, converges to exactly the integral of phi d mu. What does this mean? So, for every continuous function, phi d mu and x of 0, this is a sequence of measures, converges to integral phi d mu. Okay, this is the corollary, and what this means is that these measures converge to mu in the Weak-Star topology. That is the definition of the Weak-Star topology. So, okay, so mu n x naught converges to mu, and the Weak-Star converges to mu. So does that mean that the basin, so this means that this means that x naught is in the basin of mu. Okay, so wait, so this is for almost, so wait, so what we have here is that we fix phi, right? And then we have that for mu, almost every x naught, we have this, right? So this is now back to this issue about the order of the quantifiers, right? So here we have that you fix the you fix the observable phi, and then for mu, almost every point you have this convergence. Okay, so what I said is a lie. This is exactly the point. We don't have this yet. What we'd like is this, okay, but we don't have that right because, so the definition, so what do we need for this convergence? This, by definition of this convergence, is that for all continuous functions, for phi continuous, you have this limit, right? So limit integral of phi mu n converges to integral of phi mu. So the problem here is that we have, here we have for every continuous function, this is true for almost every point, and here we have that we need to fix a point, and we need this true for every continuous function for a given point, right? So we fix x naught. You understand the difference between these two things I'm saying? Yes. Okay. So this is almost what we want, but not quite exactly, right? This is not, this itself is not yet telling us that x naught is in the basin of mu zero. We would need to now take the intersection of all continuous functions, right? So for each continuous function, we have a set of full measure for which this holds, okay? But what we want is to find for one point, it needs to hold for every continuous function. So you should take all the continuous functions, take the intersection of all these sets of full measures, but that of course is not necessarily a set of full measure if you just blindly take the intersection, okay? And that is why we need to put a little bit of additional assumptions, which is the theorem I wrote before at the beginning, which is the theorem. So if, okay, I think we're a little bit too late for me to give the full proof, but if, so the proof, I'll just sketch a few steps, right? Proof of theorem 1, okay? The fact that mu d mu is equal to 1. This assumes that x is compact. This is what I got a little bit, I went ahead yesterday and I got a little bit confused because I was thinking ahead of what we're doing now. So if x is compact, then we have that the space of continuous functions, CF 0 from x to r, is separable. So it has a dense subset, right? And then, so let phi m in n be dense in the space of continuous function, right? And then we can apply this corollary here. So for each continuous function, so for each m in n, there exists some set chi phi m with mu of chi phi m equals to 1, okay, such that that holds, right? This says that corollary says for every continuous function, so for every m, for every phi m, right, there exists a set of full measure such that mu n of x naught, so such that we have this, such that phi integral phi mu n converges to the integral of phi mu x0, right? For all x0 in chi phi m, right? And then we can take the intersection of all these, we still have full measure. We're having a choke crisis here. So then we can define chi is equal to the intersection of all m and of chi phi m. Okay, so this is a set of full measure because it's a countable intersection of sets of full measure. So mu of chi is equal to 1. Okay, and now this has the property that we have this convergence not just for one phi, but for an infinite number of phi. Right, so here we have that integral of phi d mu n x naught converges to integral of phi d mu for all phi in this dense set, right? And for all x naught in this space, okay? And then there is a little argument which I think we're a little bit late, but I think I will leave it, but we can approximate, basically we just approximate. So then given, so for all phi continuous from x to r, let's see if I can really summarize it in just a few steps. Maybe I will just do a couple of steps here, just take 2 more minutes. So we can write, so we would like to show that we have the same thing, right? We would like to show that you have this convergence, in fact, for every phi, not just for these phi's in here. So we can write it like this. So we want to look at these averages. 1 over n is sine I0 n minus 1 of phi in xi. We want to show that this converges to the integral of phi d mu. Right? This is what we want to show, because as we said before, this is the same thing. So in fact, taking this here is the same as this. Like you can just take the time averages here, and so we want to show that this tends to 0, because that means that this tends to this, and therefore we have the mu and x, and we can just write this. We can approximate it with one of these set of dense functions, right? So we just write this as 1 over n, the sum of phi xi, plus 1 over n, the sum phi m of xi, minus 1 over n, the sum of phi m of xi, plus integral phi m d mu, minus integral phi m d mu, minus phi d mu. So I just added and subtracted trivial things here, and then we just split them up differently, right? So then we split it, we look at this, we combine these, and okay, I don't think I will. I think you can finish this on your own. You can look at the notes, but we can combine. So we write this sum of these phi xi's minus these. So we combine. We put this and this together, and then we put this phi m of xi with phi m d mu, okay, and then this here, and you can estimate. You know, because you have a dense subset, you can choose phi, right? So you can choose. So for all epsilon, there exists some phi m, right, in our space, such that the supremum of phi x minus phi m of x is less than epsilon, and then you plug this in here and you see that everything goes to 0. Okay, so I don't think it's necessary that I go through, since we're running late. But this, the key point here is that we are in a compact set, so we can find a countable dense subset, and then for each of these we get the set of full measures, and so we get this convergence for all the functions in this countable dense subset, and then we take any other continuous function and we basically approximate it by this, and so we show that we have the same kind of convergence. Okay. And this implies then the theorem that we wanted, right? So this implies that that for all continuous functions, this implies this, right? So we have now found that there exists this set here. So this set here, that is a set chi of full measure, right? And that has the property that for every phi continuous, we have this convergence here. And that means that all the points in that set of full measure, you have that mu n of x naught converges to mu, so it's in the basin of the measure. So that's how we get a set of full measure in the basin. Okay? So all this is about taking this little step of Birkhoff's ergodic theorem where almost every point depends on the function, and now you need to put slightly stronger assumption, the compactness of the space, to be able to define a set of what we call typical points for the measure. Okay, so for all those points you converge, measures converge. Okay, thank you very much. That's all for today, and I'll see you next week. These are for you.